If we look at the perspective of bulk or volume production of PV modules, this figure would suggest that thin film PV technology has become less competitive on the markets in reference to crystalline silicon PV technology. This might be true for bulk volume production of PV panels. As for such type of production and market, the metrics of both cost price per watt peak and the module efficiency to achieve low cost price for the non-module cost would be the only important metrics. However, more metrics play an important role in the integration of PV depending on its application. Therefore, many different PV technologies facilitate very different markets and applications. So the objective of this last video is to discuss these metrics and the relation between these metrics and the various PV technologies. Important metrics are, for instance, the weight of the modules. Not every roof or construction can carry the weight of glass encapsulated modules. This means lightweight modules are required as well in the market. Neither can every PV module be easily integrated on curved surfaces, so flexibility of the module might be a crucial design parameter in some applications. In other applications, you would like to cover the entire available surface, which is not possible if you only have 1.5 square meters of rectangle-shaped panels available. So customized shapes of modules would be helpful to achieve this. As discussed before, the materials to manufacture the modules should be cheap and abundantly available. In other applications, the amount of energy per surface is important, so then only efficiency would be the leading metric. For some applications, the aesthetics of the modules play a more dominant role. Color, prints, and appearance of modules might be a more important metric than efficiency and cost price. Another design metric is the shading tolerance of PV modules, which starts to play a role if the PV is applied into building elements. Also, you have metrics which depend on the climate. The effect of temperature dependence on performance of modules might be varying from climate to climate. So many different metrics are related to many different types of markets. You might call these markets a niche market, but even 1% of the current PV market would represent 700 megawatt peak of business potential. So I would like to finish the PV2X course with reviewing some metrics of the various PV technologies and so show some interesting new applications. First, we review the crystalline silicon PV technology. The big advantage is the relatively high efficiencies for modules and the low cost price per watt peak, what has been achieved by the enormous upscaling of the production capacity in Asia. An important aspect of the crystalline silicon is the reliability. Silicon PV material is very resistant against water humidity. Even in very old, poorly encapsulated crystalline silicon modules, the heart of the PV device keeps on working. The anti-reflection coating might have peeled off, but as long as the metal contacts do not peel off, the PN junctions keeps on operating under light exposure. Many PV technologies are based on PV materials or supported layers like TCOs that are not resistant against water. A disadvantage of crystalline silicon modules can be that they lack the flexibility to adapt the building geometry. It's lower performance under shading, and the modules are sensitive to mechanical stress. Bending or walking over modules might result in breaking of the wafers. The 3.5 PV technology results in the highest efficiency for devices and small-sized modules. If power per area is the most important metric for the PV integration, 3.5 PV technology is the logical choice. In case of space applications like satellite, the metric power per area and power per mass is the most important. 3.5 PV modules can be highly efficient and lightweight and flexible. For concentration photovoltaics, high efficiency per small area is the most important design metric. Therefore, 3.5 PV technology is the most suitable for concentration approaches. The challenges for the 3.5 PV technology is the cost price per watt peak due to expensive processing technology and resource materials. Alta Devices is the pioneer in coming that tries to tackle this disadvantage by new innovative processing technologies for thin film gallium arsenide solar cells. The biggest disadvantage of the thin film silicon PV technology is the relatively low efficiencies for the PV modules, making the non-module cost of the PV system more expensive than competing technologies like CIGS and cadmium telluride. For lightweight, flexible modules, thin film silicon is the cost-effective solution. As silicon is resistant against humidity, the requirements for the water barrier in the encapsulation materials is much lower. This allows much cheaper encapsulation approaches, which is usually the component that determines the cost price of flexible modules. This allows high-tech integration of modules in building elements like in this picture. This technology allows easily customized module shapes and high aesthetical applications. In addition, the multi-junction modules have a lower temperature dependence, which makes the performance less sensitive to temperature. An important advantage of the CIGS PV technology in reference to thin film silicon PV technology is that it has higher efficiencies for the PV modules. This makes CIGS PV technology more competitive in the configuration of glass encapsulated modules, like a sample here from Solar Frontiers. An advantage of CIGS PV modules is that it can be integrated in flexible modules as well. However, the requirements for the encapsulation materials are higher for CIGS. The advantage of the cadmium telluride PV technology is the relatively low cost price in combination with the fastest learning rates for the cadmium telluride PV modules. Therefore, cadmium telluride is still competitive with multicrystalline silicon PV technology. Another advantage of all thin film PV technologies like cadmium telluride is that due to the typical monolithic interconnection schemes of the individual cells and modules, the modules are less sensitive to shading effects. If the edge of the shade is perpendicular to the length direction of the individual cells, the output power scales roughly linearly with the fraction of the module area that is not shaded. Waveform-based modules have a step-like relation with the illuminated fraction of the panels and result in lower performances. For organic PV technology, several different types of modules have been demonstrated. Here you see a highly aesthetical module design from VTT Technical Research Center in Finland. The advantage of the OPV technology is that it allows to make semi-transparent PV devices and can be processed in complex shape on geometrical challenging surfaces, as you can see here. However, the challenge for OPV technology is its low module efficiency and instability of the module performance. The perovskite PV technology has similar advantages like the OPV in terms of semi-transparency up to implementation in flexible products. In contrast to OPV, higher conversion efficiency in the range of 20 to 22% have been demonstrated for perovskite PV devices with lab scale sizes of only 1 square centimeters or below. However, high efficiency for module sizes have not been demonstrated yet. The big challenge for perovskite solar cells is the instability of the device and the material. This needs to be tackled first before perovskite PV technology can be successfully scaled up on industrial level. So, summarized, every PV technology has its specific pros and cons. The choice for a PV technology for a specific PV application depends on the special conditions, requirements, and challenges of the photovoltaic application. I hope that you have enjoyed the course PV2X and that you gain knowledge and insight of the wide diversity of existing PV technologies. This knowledge will help you in the future to make correct design decisions for new innovative PV technologies and PV systems. Here you see several new applications going from the integration of PV technology in special facades, printed modules mimicking the bricks in a wall, up to bifacial modules in a noise barrier. You have now the knowledge to help in designing just such type of innovative products. But what is the impact of the position of the sun and solar irradiance on the PV module performance in real outdoor situation? The PV module is only one single component in a PV system. What are the technical specification and operation principle of the other components like inverters, DC-DC converters, batteries, charge controllers and cables? How to design a PV system ranging from a residential rooftop system to a utility-scale solar farm? What are the economics and ecology of PV system? All these topics will be addressed in the next course in the MicroMaster Solar Energy Engineering, PV3X, and this is entitled PV Systems. For now, I wish you good luck with the final exam, and I hope to see you back in PV3X, PV Systems.